everyone, my name is Amaz Ali and today I'll be presenting Lab 3 on circuits. So the main objectives of this lab was to utilize the principle of energy and current conservation to predict circuit behaviors. Some of the key fundamentals that we applied were energy conservation, current conservation, the node rule, and Ohm's law, which states that V equals IR. Our main results show that in series circuit, current remains constant while voltage drop across components. For this lab, we used a Phys simulation, which provided an ideal environment with minimal human error. Our key assumptions include negligible resistance in ammeters and wires. The EMF equals the sum of the voltage across capacitors and resistors. It is important to note that our system consists of circuit components, batteries, resistors, capacitors, and measuring devices. The surroundings are everything else, including the air around the circuit. In our results, we found the change in potential difference for the RC circuit was 5.98, remarkably close to our calculated value of 6 seconds. Let's dive into the circuit analysis. Our circuit consisted of two 1.5 volt batteries, two ammeters, two resistors, 147 ohms, and the other 100 ohms. We calculated resistance to be 147 ohms. When we placed one ammeter with a voltmeter, we observed a voltage of 3 volts, but the current dropped to 0. This is because voltmeter created an open circuit preventing current flow. In our analysis of potential differences, we found the round-trip potential was indeed 0 volts, confirming the loop rule. The current remained constant at 0.02 amps. We also graphed the potential differences across the entire circuit. Starting at 3 volts, due to the batteries, we observed voltage drops across each resistors. 0.96 across the 47, 2.04 across the 100, and these volt drops summed up to 3 volts. An interesting observation was that the ammeter readings didn't change when we added the voltmeter. This is because voltmeters have a very high resistance, typically in the mega ohm ranges, so virtually no current passes through them. They measure potential difference without altering the circuit. We did notice that when we reduced the overall circuit, the resistance in the circuit, the current increased from 0.02 to 0.06. This aligns with Ohm's law. In our measurements of the individual components, the 47 ohm resistor measured at 48 ohms, the 100 ohms, 102 ohms, both the wire and ammeter showed 0 ohm resistance. Moving on to the RC circuit, we used 10 ohms, a 20 ohm bulb, 9 volt battery, and 200 microfarad capacitor. We observed that the 10 ohm bulb starts very bright and then dims over time as the capacitor charged. The current followed a similar pattern, starting high and decreasing to 0. And the behavior can be described by the equation I equals V slash R times e to the negative t slash RC, where V is the battery voltage, R is the resistance, C is a capacitance. When we disconnected the batteries, the 10 ohm bulb lit up brightly as the capacitor is discharged, then dimmed over time. Again, the current started high and decreased to 0, following a similar but exponential decay. In our data analysis, we found that the experimental slope of our discharge curve was negative 0.167, giving a time constant of 5.98 seconds. This was close to our calculated RC time of 6 seconds. The close match between our experimental and theoretical values suggests that our ideal circuit model closely approximates real world. So, to conclude, let's consider some real-world implications. If we were to use an actual ammeter instead of our ideal simulated one, we'd introduce some resistance into the circuit. This would slightly reduce the current flow and affect our measurements. Real ammeters typically have resistance in the milliohm range. Similarly, if we use a real battery to charge a real capacitor without any resistors, our ideal model would predict instant charging. However, in reality, even the minimal resistance in the wire would cause a slight delay in charging time. Real-world capacitors also have internal resistance, which would further affect the charging behavior. These considerations highlight the importance of understanding both ideal models and real-world limitations in the circuit analysis. In practice, we might need to account for internal resistance of batteries, capacitor leakage current, temperature effect on component behavior, electromagnetic interference, and sensitive measurements. That is all, folks. Thank you.